Question 17 is about alpha amino acids. Now you should know what the general structure of an alpha amino acid is, but just to be helpful they've given you that representation of it. And the first bit, it asks you to take one example where R is CH2SH, which is cysteine, and it asks you to draw the optical isomers. So remember that optical isomers have to be represented with three-dimensional pictures, and the best way to do that is by just practicing drawing a tetrahedron like that, and then you just draw the mirror image of that tetrahedron like that, and then all you have to do is identify the chiral carbon and put the four things that are around that chiral carbon around it in the picture. So the particular one that we're looking at is cysteine, where R is CH2SH, so we've got SHS CH2 there, and of course that's not the chiral carbon, this one is, and that's the case in all but one of the alpha amino acids, that central carbon there is chiral because it has four different groups around it: a hydrogen, an amino group, a carboxylic acid group, and whatever the side chain is. So that's the one that goes in the middle there. And then you just put the four groups around it wherever you want on this first one. So let's, for example, put the hydrogen there and the NH2 here, COOH, making sure that you get the connectivity from carbon to carbon. Okay, if you wrote it like this, it would be wrong, because that makes it look as if the bond is from the carbon to the hydrogen. So you've got to be very careful with the groups on the left-hand side of things. So we get COOH like that. And then we have the CH2SH group at the top. And then this one, you just draw the mirror image of that. So you imagine, or if you like, you can draw a mirror line down there, and you just draw the exact reflection of that in the mirror. So this hydrogen here maps onto that position there, and the NH2 maps onto there, and so on. So it's very straightforward just to sort of view it as if it were a sort of GCSE maths exercise, doing a transformation like that. This one you can draw in a mirror image relationship if you want to, although because you can rotate around that bond you don't have to, and it's probably easier just to draw it like that. Okay, so those are the optical isomers. So practice that, because once you know you can do that, those are dead easy questions. B is now asking us about a different amino acid, lysine, which has a different R group. So again, make sure you read the question carefully and registered it's asking about a different one. And this one has four CH2s and then an NH2 there. So, you know, you could draw it like that, but it's messy. I hate these kind of structural formula representations. So I would be inclined to redraw that as a skeletal formula, or at least something a bit more explicit than that. You know, just something as simple as this would be fine, because it's just so much clearer than what's going on. Okay, so that's your starting amino acid, and it's asking what happens if you react that with excess dilute hydrochloric acid. It's the third time in this paper we've had this idea of excess, that it's going to react more than once. If you're not picking up on that clue, you could lose a lot of marks, because it usually implies that it's reacting more than once. And that's the case here, as you can see, because you have two amino groups, and amino groups are bases, so that if you add acid they will simply react to form a salt. So all that happens if you add HCl, remember that the lone pair on the nitrogen picks up H plus from the acid, so NH2 becomes NH3 plus, and the same here, that NH2 becomes NH3 plus. And you have to be careful because it asks for the structure of the salt. If it had just said the organic product, you could have got away with just writing that down. But because it says the salt, that means the whole compound. So if you just draw that, you're going to drop a mark. You've got to put the chloride ions on as well. And of course you know the chloride ions because it was hydrochloric acid that you added. And so that's it, that's your answer. Part C gives us this perhaps slightly scary looking chunk of protein and asks us what happens when we hydrolyse it with hot aqueous sodium hydroxide. So the fact that it's a protein is not relevant from the chemical point of view. The idea that there was something magical and different about biological molecules disappeared in the 18th century. So from our point of view, we just got to look at what functional groups it has, and the key thing to recognise is that that is a secondary amide group. And that's what proteins are. They are polymers of alpha amino acids. So let's just kind of remind you of how that works. So if you have a pair of alpha amino acids like this, so we have H and R and COOH. Okay, so there's one. And then you have another one here. Okay, with the same kind of structure. It might have a different side chain there, so we'll call it R prime, but it's got the same layout. Okay, so the way you join them together is by condensing the carboxylic acid group here and the amine group there. So specifically, if you draw them back to back like this, you can see the OH from the carboxylic acid group and one of the hydrogens from the amine group are condensed out, so they will disappear, and what you get is a linkage then between the carbonyl and the NH. And that's what's happened in the middle here. And of course, because you have another carboxylic acid here, you could put another amino acid and condense it on there, and another one and condense it on there. So hydrolysis is just the reverse of that. It's saying that wherever you get one of these bonds, you break it, break up the amine, and you restore those groups where the carbonyl group was to being a carboxylic acid, and where the amine group was, or where the NH was rather, to being the original primary amine group. So it's very easy to figure out what happens with hydrolysis because you just do that. The only thing you have to be careful of is to take account of the conditions, because in hydrolysis reactions they care about whether you're doing it under acid or alkaline conditions because it slightly affects the product. And the exam board is very inconsistent. For most reactions where you have groups that can be protonated or deprotonated under the reaction conditions, they don't really care. But for hydrolysis reactions of esters and of amides, they do. And you just have to be aware of that. So having worked out that this is the pattern of hydrolysis, you just break open the CONH group like that, you then think, right, this is alkaline pH, so is either of those functional groups I've created going to be affected by that? And of course the answer is, well, yeah, because this is a carboxylic acid, so at alkaline pH that's going to become COO minus, and because it's sodium hydroxide it'll be specifically COO minus Na plus that's formed. The amine group, well, that's not acidic, so that's not going to care about the alkali that's there. Okay, so now we can apply those principles to this compound. So that's a linker bond, right? So that's going to be in the protein connected to the next carbonyl group along, okay, from the extension of the protein. And so when we do this hydrolysis, that bond is going to break, and that NH is going to be restored to being an NH2. Okay, so that's what's happening at the left-hand end. Then we come along to here and we say, right, here is our amide group. So we do exactly the same thing. We say, right, that amide bond is going to be gone, and instead we're going to have COOH. We'll worry about the alkali in a minute, we're just reversing the hydrolysis for the moment. So we'll have COOH there and NH2 here. So the same thing as we did down there. And here this COOH is going to be connected to the NH from the next amino acid along in the chain. So again, that bond is going to be hydrolyzed, and you're going to get that restored to COOH. And that's the backbone of the protein deconstructed. The next job is to think about the alkali, and remember that, yeah, it doesn't affect the NH2 groups, so those we keep the same, but the carboxylic acids, because it's in sodium hydroxide solution, then just as we did down there, we change those into COO minus Na plus, because it'll be the sodium salt that's formed. Okay, so that's what you get. Now, the complication with proteins is that you have these side chain groups sticking off as well, and we have to worry about, are any of those going to be affected by the alkali? Now this one is an alcohol, and you need to know that alcohols are not acidic. Phenols are, carboxylic acids are, those kind of OHs would have reacted with the alkali, but alcohols are not. So that one will be unaffected, so that's no problem. Then we have this big side chain here, and you have to look at this group at the bottom and realise that's another amide group. This time it's a primary amide rather than a secondary one, but it's the same idea, that you can imagine a primary amide being made from a carboxylic acid and ammonia. Like this. Okay, so to make CONH2, it's the exact equivalent of what we did to make the secondary amide, but instead of a primary amine here, you just have ammonia, and again you condense out the OH and the hydrogen, so we lose that hydrogen from there, we lose the OH from the carboxylic acid, and we make a bond like that, and that's what that functional group is there, a primary amide. So again, under the hydrolysis conditions, that's going to be reversed. So we do exactly the same as we did with the secondary one, and we say, okay, where the CO was, that's becomes COOH, where the NH2 was, that becomes NH3, and then you think, but it's under alkaline conditions, so are these things affected by alkali? Well, ammonia isn't, it's not acidic, but again the carboxylic acid is, so it's the same pattern each time. And so what that means is that we don't need to draw the ammonia because it only asks for the organic product, but we do have to draw the fact that this has changed now into COO minus. Okay, now seeing that for the primary amide was perhaps a little bit tricky. We don't meet those very much at A level, but this bit you need to be very confident, so make sure you learn ester hydrolysis and amide hydrolysis from your notes, because they're very popular questions.